Hello. Hi there. Last year at BritPave, I think one of my colleagues, Lisa Scullion from Manchester University, so I'm not from Manchester University, but yeah, we've done a lot of work with her. And she, I think, did a broad overview of graphene and the applications of graphene and stuff that's done on the lab scale. So you'll all know about graphene, so I can jump right into the project that we were working on. I'll do a bit of an intro on graphene as well. This is all about a project which was run with funding from Innovate UK. It was with Morgan Sindall, Breedon Cement, and the University of Manchester and First Graphene. And it was all about looking at how you can enhance cement with graphene. This is just a little bit about us. So why has it fallen to us? There's not really any other projects looking at graphene and cement at the sort of scale that we are looking at. And how have we ended up in the position where we're able to do this at scale? So First Graphene's an Australian company out in Perth in Western Australia. That's a picture of our plant at the top right. So we produce graphene from graphite. So graphite is broken down using an electrochemical exfoliation process. So we basically apply a charge to graphite and form thin sheets of graphene. We have a plant there which produces 100 tons of graphene per year. Now, not a huge amount in terms of cement production, but it is enough that we can run some pretty beefy trials here in the UK. That's what our plant looks like, that's what our product looks like. It usually comes in bags. We supply it to all kinds of other industries as well, but I mainly work on cement and concrete and energy storage materials. You can see we have a different range of products. So that's like a graphene paste, so it's the same platelet. I'll show you some images of the platelets. So this is what it looks like in real life. So you've got this powdery material, that's when it's dry. You can see here on the right in that moving image, that's a graphene paste. So that's graphene mixed with water, so that can go into aqueous applications like coatings and also into the cement. You can see there at the bottom left, that's what it looks like under the microscope, these platelet structures. So it's like it's a microscopic platelet, very, very thin, but very large aspect ratios. And then that colored image is just showing you that it's mainly carbon. There's some oxygen functionality on the edges, but this is the material that can go into all these sorts of applications and give you multiple benefits. You can see there on the right, that's my R&D manager, Ian, handling the graphene there. So you can see we're doing it at a pretty large scale for graphene. These are some of the benefits. The ones that are most relevant for cement and concrete are that, one, that it's strong, also that it's small, and that it can provide a nucleation site during cement hydration, but that's not on here. But yeah, it's also a very small material, it's a nanomaterial. It's very strong, so the tensile strength is very high, and it's also totally impenetrable. So it's impenetrable to even things like hydrogen or helium. It can't pass through it. So that means it's a very good water barrier, it's a very good ion barrier, and it can impart the properties of graphene, so the very high strength can be imparted onto the cement matrix, and that's what we're really trying to improve in the concrete, is that strength of the cement paste. Nothing really to do with the aggregates, but just enhance that cement paste and the cure of the cement there. So graphene's been talked about for 20 years now. The Nobel Prize was won in 2004 for graphene. And why are there so few applications where graphene's actually used at scale? This is just to give you a bit of an overview of why it's so difficult. So graphite is the most thermodynamically favorable form of carbon, so it wants to restack into graphite. All these layers, all these graphene layers, they want to restack and they want to form graphite. And so when you get graphene and you make a product out of it, or you sell it like we do in a paste or a solid form, it wants to restack like the image on the top left. It wants to form these graphitic lumps, and they're no good. That's useless. That's just like putting graphite into your mix. There's no point in doing it. If anything, it might make it weaker. The graphite will cleave along those planes, and you'll actually make it weaker. So we want to make it more like D, where the cement is bonded directly to the platelets. That strength is imparted onto the cement paste, and the tensile strength of the graphene platelets brings a benefit to the hydrated cement. And doing this is very difficult, and it's difficult to supply a product which is stable. It's a formulation issue, really, that you've got to supply something stable and in those single platelet forms, which is suitable for all applications. And that falls to us, really, as the graphene supplier, to work on these different formulations and make sure our graphene is applicable to whatever end goal that we're trying to achieve, so whether it's polymers or whether it's cement and concrete. So getting that D image there is quite difficult, especially in cement and concrete, when you don't want to use surfactants, and you've got to try and prepare that dispersion in a different way. The microscope images there on the left and on the right shows you just the difference under the microscope between a well-dispersed graphene mixture, which is active, and all those small platelets are active and accessible, and the one on the left, which is, they're all in that graphitic sort of form. There's no free platelets there to bond into and to provide you the strength. So this was the main bulk of the project. So this was a Transforming Foundation Industries project. So the aim was to try and get graphene into cement and then into a slab. And so that's just the images of the process there. So we took our graphene, we mixed it into the grinding aid. Really, that was the key point in the project was, how do we get the graphene into the cement plant? Usually when you've got graphene, you need a liquid addition point, so you need to get it well dispersed before it goes into the cement plant. And there's only really one point to do that. You can put it into the water, which is sprayed into the cement mills, but you could there's also existing grinding aids which are used inside the mills. So we thought that is really the only point in the cement production process where liquid additives used. So we need to target that point, get the graphene into that grinding aid, disperse it well, and immediately dose it into the mills. So you can see here that on that middle right image, that's one of the mills at Breedon Cement Plant, and that was our little gazebo there where we did our dispersion process. And I'll show you inside the gazebo, there's nothing secret there. So we added that grinding aid, we dispersed it, dosed it straight onto the belt, it went into the mill, and then from that point on, it was just like a regular cement. So no one down the supply chain had to worry that there was graphene in that cement. They just treated it as normal. There was nothing unusual happening there. So that's one of the tankers that contained 30 tons of the cement, but we actually made about 1,000 tons in the trials. So we worked with the University of Manchester. They were looking after the lab activity. They were looking at the CO2 footprint of the cement and of the graphene and and of the mixture. They were looking at the health and safety aspects of having a nanomaterial in the cement, something that's not been done before. Breedon were in charge of the cement production and the logistics and getting it to the batching site, and then Morgan Sindall were in charge of looking after the concrete batching and pouring it into the slab, which you'll see some images of. So this is the dispersion process. So all that effort that goes into getting these platelets active and in that grinding aid went through this process. So we started with our standard graphene powder. We passed it through a high pressure homogenizer, which is used in milk processing or emulsification processes where you want to mix oils and water. And we passed it through that process, and what that does is it's a very tiny aperture in that mixer, and you apply about 1,000 bars of pressure to it, and as it goes through that tiny aperture, there's huge shear forces in there, and all those graphitic lumps, they get dispersed, and then you form your nice individual graphene platelets, and they're dispersed into the grinding aid. We then went on and did lab testing in these small-scale cement mills. So you can see there the grinding aid, that's that black paste there with all the dispersed platelets. Once you start to disperse the graphene, it has a very high surface area. So even low loadings of graphene in a dispersion will cause it to really increase in viscosity as that surface area is exposed. That's it in there with all the additives, the clinker and the gypsum and the limestone. We passed it through the ball mills. I won't show you all the data, but there is some, we saw decent trends in the data. So at early ages, so at, you can see here where we're looking at firstly, the graphene loading on the left. So how can we optimize for graphene loading? You can see it goes up there. So you add graphene, and then it reaches an optimum. We found this in literature as well with our materials. We've done a lot of work with Australian academics. And they also found that this optimum occurs. So at 0.06, 0.07%, at very low loadings, you start to see a peak in performance. So, and then when you add any more graphene, it starts to drop down again. So it could be something to do with the nucleation efficiency of the graphene. It could be something to do with there's too many agglomerates still in there, there's too many graphitic-like particles, and then that causes a decrease. So that we always see this hump at very low loadings. We also looked at the effect of the grinding aid. So the grinding aid is just like a liquid. It's just like water, it's very low viscosity. So when we added graphene into that and then dispersed it, the viscosity shot right up. So we had to add some extra water to get that flowable again, because it had to pass through existing equipment on the Breedon cement plant. So that's what the one thing we wanted to do, is use as much existing equipment inside the cement plant as possible. So we were doing this dispersion, but then the viscosity shot right up, so we have to add some extra water to keep it flowable. So we're just making sure that none of that has a detrimental impact, and we also did some tests with some polymer surfactants, just some PCEs, to just see if we could get an even greater improvement. We ended up not using the polymer surfactants in the trial, just the graphene and the grinding aid and the water, and that was able to be pumped in. So why is there an improvement at all? So really, it's all about, we did some in-depth investigations into the cement paste. So we took graphene and cement and water, and that's it. That's all that's in these samples. This was just a SEM1, so we wanted to see what the effects of clinker hydration and graphene had on the hydrated area of these images. So we were looking at so we just took the cement paste, polished them, infused them with resin, polished them again, and then so we get images like this on the right, so very flat cross sections of the cement paste. You can see here on on the images, you've got the unhydrated cement particles, the lighter images, the lighter parts of that image, and then you've got the holes, which are the dark parts, and then you've got this intermediate hydrated area. We worked with Nick Winters, I don't know if you know him, but he looks at SEM images of cement from cement plants all across the country, and we used his guidance to try and identify what areas were the hydrated areas and monitor them. So basically we were looking at the improvement in hydration with the graphene addition. So with standard SEM1 samples, we were getting about a 69% hydrated area, and then with any sample containing graphene, all samples containing graphene, there was always an improvement in the hydrated area percentage. So we think that's why there's these improvements in strength. One, because of the nucleation effect, but two, because these nucleations are happening on particles with very high tensile strength. So that's why we think this is happening. So how does this help us reduce CO2? So that was the aim of the project. Transforming Foundation Industries is all about looking at cement, concrete, glass making, steel making, and looking to see if we can reduce the CO2 impact of those industries. So this is what the university did. So they did a full life cycle analysis of both processes, the cement production process and our graphene manufacturing process. And this is the kilos of CO2 equivalent per ton in each of the products. So you can see here, this is published, so it's not a secret, but you can see on Breedon cement, it was 775 kilos of CO2, and in our graphene, it's 121,000 kilos of CO2 per ton. Obviously, that's huge, and this was one of the outcomes of the project, was to identify how much CO2 our graphene, or how much embodied CO2 our graphene had. Now, we've worked on this process, and we've brought that down by about 75% now. This project started about 2 years ago, and the life cycle analysis was one of the first things that was done. So we've already started to optimize our process. Have I put images in here? No, I've not. But basically, because our site's in Australia, Australia has a very dirty grid, so it's fueled by coal and lignite, so it's the worst place to put an electrochemical exfoliation plant. So we can basically move the plant anywhere else in the world, and we'd get a much lower CO2 output. Somewhere like France would reduce our CO2 footprint by about 90%. We could also just install solar panels or something like that to reduce our CO2 footprint and then reduce the embodied CO2 of graphene. So the university also looked at, so now we've got this very high CO2 footprint of the graphene and moderate CO2 comparatively of the cement. So is there actually a point where you can add graphene and still get a CO2 benefit? So yes, dependent on the strength improvement and the amount of clinker you can reduce in your cement. So really the target of the project was to produce a CEM2, a limestone cement with a 52.5 N strength class. So it was trying to improve the existing 42.5 N strength class up to 52.5. And then that could start to replace some of the applications where a CEM1 was used. So really, that's where we're looking at here is we want to try and get a percentage improvement so you can reduce the clinker, add more limestone, and is there an offset? So you can see on some of these lines here, if you get a 10% improvement or a 20% improvement, how much CO2 per ton you can offset with a specific loading of graphene. So these have changed again since the life cycle analysis was carried out. This is the worst case scenario. If you start to load 0.04, 0.06% of graphene and you get a 10% improvement, then you can see there that you can still save a few tens of kilos of CO2 per ton, but obviously we've moved on since then, and it's a much more efficient process. So we might have to rerun that life cycle analysis with the university to get to make this chart look a little bit better. Oh yeah, that's the electricity demand for our process there. So you can see there that the Australian grid is just incredibly dirty there. You can see that it's on a par with China. So this is the practicalities of what went on, so how we went through the process. So we started with, we used Fosroc, so we partnered with Fosroc from a grinding aid point of view and from an admixture point of view. So we found a Fosroc grinding aid which would be suitable for breeding, so optimized what the chemicals which are in there. Fosroc did that optimization and they provided a grinding aid to breeding. That was trialled, so that new grinding aid, so this isn't Breedon's existing grinding aid, this was a new grinding aid that was being trialled, so it was there supplied in those IBCs, and we tried a few different load-ins, a few different optimizations. So this is without the graphene. So we had to do that baseline check to start with and see how the grinding aid performed. Then this is our graphene, so this is the 7 or 8 pallets of graphene which was dispersed into that grinding aid. So that's the pallets on the left of graphene, someone unpacking the pallets there on the right, and that just went into a big tank and it was just loosely mixed. So that was a powder in those boxes, powdered graphene, went into the mixer, and it was just a paddle mixer. Again, no high shear, no dispersion, really just mixing it round so that it was in a liquid and it was easy to handle by the pumps. Then we used our special mixer, just like we did at the lab scale. So we used this high pressure homogenizer. We set it up in that tent there. We had the IBCs, which had the graphene and the grinding aid, not well dispersed, passed it through that high pressure homogenizer to blast apart those graphitic particles into the graphene platelets, and that was dosed immediately onto the belt of the cement mill. So the grinding aid just goes on top of all the raw materials for the cement mill. And then at that point, it's business as usual. We did some trials, so we took about 20 different samples out. Obviously this was running for about 8 hours. We used a ton of graphene in that trial. That was powdered graphene, so it's very low density, so that's why it looks like so much in those pallets. Those 7 or 8 pallets there, but it only had about a ton of graphene in it because it's very low density. So we got this data here. So I couldn't give you the absolute numbers for the cement plant, but I can give you a relative improvement. So this is the relative improvement at early ages, which is what we were targeting. You can see there it was between 2.5% and 10% improvement at early ages. For this specific load-in, obviously, there's a lot of optimization before that, before we went on to the final trial. And then after that, it just went into tankers. It went to the site in Margaretting there, so Morgan Sindall were able to work with the batching company. It went into volumetric trucks, so this is the cement being delivered to the batching company, put it into volumetric trucks. It went up there to the Margaretting junction of the A12, and that's it being poured into the temporary works there, and we were able to just build that confidence that nothing unusual is going to happen with this concrete. Yes, it's a new additive, but it is just an additive, just like anything else. It's not anything too high tech. There is a bit of work that's required on dispersion, but it's not an unusual. It's just an additive, just like anything else. And the concrete performed as we would expect. The slab we got to visit a few months later. It was cored. You can see there 2 images of the surface, the unworn and the worn surface. It was 150 truck movements a day. This was over a wheel wash. This is a wheel wash slab. So a pretty brutal condition, a test scenario for this concrete. And yeah, so it performed adequately, just as you would expect. There was nothing unusual happening there. The cores looked fine. The surface looked as worn as you would expect. So yeah, there was nothing unusual there. Obviously, we're moving on, and we're going to do another trial. So this is our new product. So we're using the graphene paste this time. We don't need to use this special high-pressure homogenizer. We're going to dose it into the mills using this auger pump, which is much simpler. It doesn't require as many people on site to keep an eye on it. So this is a much more scalable solution. Obviously, we don't sell the pumps or anything, but we just want something that's easy to use and for breeding to really have minimal input on. Just have a button that says, right, okay, we want to turn on a graphene enhanced batch or not, and just start the auger pump or not, and we just have a silo full of graphene and it'll just flow into that auger pump. We've also got a new pour site, so Morgan Sindall, we're still involved, so there's no more funding for this project, but obviously everyone's still working together on this, which is really good. So that's what you want. You don't want a project to run for 2 years and then just end when the money runs out. So it's really started something here. So we're going to run another trial with no funding. We'll work it out ourselves, how we get that done. But yeah, that graphene's now on the water, so we're ready to go for this new pour site and for this new graphene enhanced cement. I think that's everything. Yeah, that's it all. So thanks very much. Yeah, no, it's no problem.
Any questions to present to Michael, please? You've stunned them by
that's all right.
the excitement of it all.
It's all good.
But this is exciting, that there's this whole new process, whole new cements coming out, and led by Michael's presentation and the other two to follow. I keep feeling a Star Trek theme coming, to boldly go. So thank you, Michael.